I guess we'll kick off anyway. My name's Max. Welcome to an intro to GLIBC heap exploitation. My mic is on. Those VMs should work with both VirtualBox and VMware. If you're using VMware, you might need to click the retry button once while you're importing because software. Once you've done that, boot them up, full screen them. It should log in automatically. But if they mess you around, the username is HeapLab, which is lowercase, one word. Password is exactly the same as a username. If you want to change your keyboard layout for whatever reason, because you're using a US keyboard like mine, there's a text file called useful commands in the home directory of each of these VMs that contains instructions on how to do that stuff, and plus make some more quality of life changes to the VM as well if you fancy doing that. So while you guys are getting that wrapped up, I'll give you a brief description of what we're doing here today. So for those of you unfamiliar with it, GLIBC stands for the GNU-C library. It's an open source library, takes the form of a shared object. That's the Linux equivalent of a DLL. And it's been a fundamental part of most Linux operating systems for the past 30 odd years. It's used in hundreds of different distros, both desktop and embedded, including popular distros like Ubuntu, Debian, and Arch Linux, to name just a few. And all GLIBC does is provide some boilerplate code, functions like memcopy and printf, to programs written in C and C++. And by extension, higher level languages like Python, whose interpreters are often written in C. So simply put, on your average Linux distro, you'd be hard pressed to find a process that doesn't map the GLIBC shared object into memory. And included in that boilerplate code is a dynamic memory allocator, known as Malloc. And dynamic memory allocators are used when a program can't know the size or number of objects it requires prior to runtime. Malloc's job is simply to dish out so-called chunks of that heap memory, of dynamic memory, I should say, to these processes at runtime. And those chunks come from large contiguous blocks of memory called heaps. If you guys have ever dealt with strings in C, you've almost certainly used Malloc. In C++, you're a little more abstracted. The new and delete operators are thin wrappers around Malloc, as are by extension make shared and make pointer, make unique. So the fact that Malloc is so widely used, combined with the fact that it's used in languages like C and C++, which still have issues with memory corruption, make it a great target for exploitation. And that's what we're doing here today. We're going to learn two heap exploitation techniques. The first is called the House of Force, and the second is known as a fast bin dupe. Our tools are the trade of the GNU debugger, GDB, enhanced with a Python library called PwnBag. And to help us interact with the vulnerable binaries we'll be exploiting, a second Python library called PwnTools, that I'm sure a lot of you are already familiar with. So, switch fire to your VMs. Open up a terminal by clicking that black icon in the taskbar. We'll kick off with some Malloc internals. Now, Malloc itself is just a collection of functions and metadata for the purpose of dishing out those chunks of heap memory to processes. And today we're only concerned with two of Malloc's functions. Malloc itself for requesting heap memory and free for recycling it. It's a little confusing to have a function called Malloc used to request heap memory from the dynamic memory allocator, also called Malloc. But at least it's a simple function. It takes a single argument, the size in bytes of memory that you want, and it returns a pointer to that amount of memory or slightly more for you to do with as you wish. So, help us visualize how heap memory is requested via Malloc. We're going to debug a small demo binary. So, from your console, navigate to the House of Force directory. Can you guys read that, incidentally? It's big enough on the screen. Happy days. In which you'll see a collection of binaries and scripts. We're going to debug a demo binary under GDB with the command gdb demo. Once GDB is launched, issue the start command. That'll set a breakpoint on the main function, and then run the binary. Welcome to PwnBag. If you've used other GDB enhancement suites like Pedder or Gef, you'll be right at home here. And there's a lot going on the screen, but all we're concerned with is the source panel, that third one from the bottom, in which we can see that all this program does is use the malloc function to request different amounts of heap memory, starting with this first request for 9 bytes, and storing the return value in a variable called A. So before we let it do that, we're going to introspect the heap. The vmmap command prints a virtual memory map of this process. And from the legend at the top, we can see that the heap should be colored blue. But there's no blue text. That's because malloc won't request heap memory from the kernel until it actually needs it. So we're going to issue the next command, which can be shortened to N, to execute that first request for 9 bytes. Now the output of the vmmap command should show us that we do indeed have a heap, address hex 405000, and it's about hex 21000 bytes long. That's about 135,000 bytes. And to introspect that heap memory, we're going to use the viz heap chunks pwnbag command, which can be shortened to viz. And I'll do my best to explain what we're seeing here. That yellow region, consisting of these 4 quad words, is a chunk returned by that first call to malloc, that first request for 9 bytes. We can confirm that with print A, which can be shortened to just PA. That's the return value from that call, hex 405010, which is this address here. That's the first quad word of this chunk's user data, consisting of these 3 quad words here. First thing you notice is that we got more than 9 bytes. 3 quad words at 24 bytes, to be precise. Turns out that's just the minimum chunk size that you'll get from malloc. If we use the next command again to request just 1 byte via the malloc function, the viz command shows us that this turquoise chunk that we got also has 24 bytes of user data. Even if we use the next command to request 0 bytes of heap memory, output of the viz command shows us that this purple chunk, this magenta chunk, also has 24 bytes of user data. So minimum chunk size, 24 bytes of user data. You might also be wondering what these values are here, part of the same chunk but sat just before the user data. Well, that's because malloc uses inline metadata, meaning that much like how some stack metadata like, say, base pointers and return addresses are stored on the stack itself, malloc stores some of its heap metadata on the heap. In this case, this is a size field, and it represents the sum total of bytes that make up this chunk, user data plus the size field itself. So in these cases, 24 bytes of user data plus 8 for the size field is 32, or hex 20. But we're seeing hex 21 values on this heap. And that's because malloc chunk sizes increase in increments of 16 bytes. So for example, if we use the next command again to request exactly 24 bytes of heap memory, viz command shows us that this green chunk that we got gives us, as expected, 24 bytes of user data. But if we use the next command again to request 1 more byte at 25 bytes, viz command shows us that this blue chunk that we got is 1 chunk size up, so a hex 30 size chunk with 40 bytes of user data. And the fact that malloc chunk sizes increase in these increments of 16 bytes means the low order nibble of each of these size fields is never used to indicate the size of these chunks. That way it can be used for flags. In this case, the least significant bit of each of these chunk size fields is set, indicating the prev in use flag, which simply means that the previous chunk, that adjacent chunk in lower memory, is in use. Since all of these chunks that we have here are in use, all of their prev in use bits are set. You might also be wondering why this first chunk didn't start here, at the beginning of the heap. Well, technically, it does. From malloc's perspective, all chunks start 16 bytes before their user data. So even though this yellow chunk's user data starts here, according to malloc, it starts here. And malloc chunk shapes, at least when viewed like this, are variable, and they depend on a few factors, including the size of that chunk, whether that previous chunk is free, whether that chunk is free, and the size of the previous chunk as well. And the malloc maintainers understand that this is a little confusing. Indeed, in the malloc source, alongside the chunk struct definition, there's a comment that reads, "This chunk struct definition is misleading," but necessary. Fortunately for us today, we're just going to deal with this kind of offset chunk shape that we're seeing here. Lastly, I'll draw you guys' attention to this region here, labelled the top chunk. You might recall from the output of our VM map commands that this heap is about 135,000 bytes long, but we're seeing perhaps between 1 and 200 bytes of that here. That remaining as yet unused heap memory is treated by Malloc as one large chunk that it calls the top chunk. And every time we've requested heap memory from Malloc, it's broken off a piece of that top chunk and converted it into a smaller chunk and given that to us. And Malloc will keep doing that until the top chunk is exhausted, at which point it will try and replenish it. And to keep track of how close the top chunk is to exhaustion, it also gets a size field, this value here. And no, go ahead.
The top chunk is the amount of memory that's allocated by Malloc.
The top chunk is the remaining memory, precisely. So yeah, you're right, it starts off as one big top chunk. So that would have been about 135,000 byte top chunk. But every time we request little bits of memory from it, it breaks those off. And that remaining memory is just called by Malloc the top chunk. Top chunk, even though it seems like it's the bottom here, it's the highest in memory. Basically, it will always be that highest chunk in memory. So interestingly enough, aside from the most recent versions of GLIBC, that top chunk size field is not subject to any integrity checks. And this forms the basis of our first technique, the house of force. So with that in mind, close your debugging session with quit or Control D. And we're going to run the house of force binary. So go ahead and run that on the command line. This is a small CTF style binary written in C. It's got a heap bug against which we're going to learn and leverage the house of force technique. So have a play with it, see if you can find the bug. And while you're doing that, I'll explain what's going on. So I'm going to run my copy under GLIBC so we can introspect memory. So once I've started GLIBC, I'll use the run command to start the binary. First thing we can see it does is leak a libc and a heap address, which is awfully convenient. Heap corruption can allow you to leak both libc and heap addresses. We're going to let this binary do the heavy lifting for us today so we can focus on the technique at hand. And below that is a small numbered menu. Option 1 allows us to request chunks from Malloc, up to 4 of those. So if I hit 1, I can request a size. I'm just going to go for 24 bytes to give us a minimum size chunk. And then I can write some amount of arbitrary data into it. So if I break in GLIBC with Control C, follow that with the viz command, I can see that as expected, Malloc's given me a minimum size chunk, a hex20 size chunk, with the prev and use bit set, and it's written my capital Y's, these hex59 bytes, into that chunk's user data. If I continue with C, option 2.
Sorry, how did you get to this?
Sorry, I started the binary under GLIBC, so with GLIBC house of force.
Yeah.
And then I did run to run the binary. I picked that first option, and then I hit Control C. So Control C allows you to break in GLIBC like this, and then C for continue allows you to just crack on.
Sorry, just to double check as well, the blue bit of memory that we see in the beginning.
Yep.
What is that for?
So technically, that's part of the same chunk. It's just that Pwnbag has decided to color it a slightly different color. Essentially, as I mentioned earlier on, chunk shapes vary. And as we'll see with our next technique, different parts of the chunks get repurposed as inline metadata. So although we won't come across this today, that might end up being repurposed as something called a prev size field, which indicates the size of the previous chunk. But because there's no chunk before it, that's dead space. Like that'll never get used because that chunk doesn't have a previous chunk because it's at the beginning of the heap.
Cool. So those first 2 chunks that we see are part of those essentially metadata fields that will then
Yeah, precisely. Yeah, like I said, something will be user data 1 minute, and then when it's free, it'll be repurposed for metadata. Awesome. It's good. Malloc's really efficient. It uses space very efficiently. So, option 2 prints the target, which is this short string of capital X's that resides in the data section of this binary. The binary is non-position independent, so we know the address of that target at all times. And our objective is just to overwrite that string of capital X's so that when we hit the target option, it'll print our data rather than that string of capital X's. Now, overwriting strings isn't very sexy, but it allows us to prove that we can leverage this house of force technique for an arbitrary write. And arbitrary writes are powerful primitives, and you can build on them to get arbitrary code execution, for example. So, has anybody found the bug after messing with this binary? Well, I can tell you that there is a small overflow when we read data into these chunks. So if I pick option 1, and then again just go for a minimum size chunk, I can spam a load of capital Y's, because why let the capital A's have all the fun? And then I can break with Control C, and then the output of the viz command shows us that I got another hex20 size chunk. I read 24 bytes, or the program read 24 bytes of my capital Y's into the user data, and the last 8 of which overflowed into the top chunk size field. So it's an 8-byte overflow. We could argue all day as to whether that's a realistic bug, but bear in mind that that last quad words of the last chunk to be allocated's user data butts right up against the top chunk size field. So an off by 1 in an array of longs, for example, might be able to overwrite it. Either way, we've got a bug whereby we can tamper with the top chunk size field, which, as I mentioned, is the precursor to the house of force technique. So Malloc's going to treat this as a size field, so we can either make it a small value or a large value. Making a small value is a valid part of some heap exploitation techniques, but today, for the house of force, we're going to make this a very, very large value. And I'll show you why. So this is a simplified virtual memory map of our process, much like we saw from the VM map command. Typically, in x86 Linux, you'll have the application at lower addresses, followed by the heap in a region known as the program break, libraries and stack at higher addresses. Each of these are typically in their own ASLR zone. They are, in this case, we have a heap and a libc leak, and the binary is non-pick. So if we were to overwrite the top chunk size field with a very large value, that will convince Malloc that that top chunk, and therefore that remaining memory of the default heap, is much larger than it really is. And potentially, we could request a very, very large chunk that ended up overlapping allocated data, potentially sensitive data in libc in the stack. We could even request a really large chunk that wraps around the VA space and overlaps memory at a lower address than the heap, including our application where the data is stored, where our target data is stored. And that's exactly what we're going to do. We're going to set that top chunk size to a very large value with our 8-byte overflow, and then we're going to make a large request that spans the gap between the top chunk's current location and our target data. We're going to stop just shy of the target data, and then the next small request we make that's going to get broken off of the top chunk, or what Malloc still thinks is the top chunk, is going to overlap our target data, at which point we're going to overwrite it. So to do that, we're going to need to do some stuff like send non-printing characters to this binary, and we'd like to make it repeatable as well. So this is where PwnTools steps in. So Control D or quit out of GDB if you had that running, and make a copy of the PwnTools template Python script. I'm going to call mine xpl.py, short for exploit.py, also makes tab completion easier. You guys can call yours what you want, with the exception of pwn.py. People seem drawn to calling their exploit scripts pwn.py, but the first thing these scripts are going to do is from pwn import star. Your script will try and import itself, and the universe will implode, or so I'm told. So once you've made a copy of that PwnTools template script, open it up in a text editor. I'm going to use Vim. You've also got the option of Atom available via this green icon in the taskbar. Can you guys read what's going on there? Don't be alarmed. There's a lot of text on the screen, but everything we're seeing there is PwnTools boilerplate and some helper functions that I've written to avoid this becoming too much of an exercise in Python. If you scroll down to the bottom, all we care about is the stuff between these dash lines here, which currently is just some example stuff that we're going to delete shortly. So the heap variable in this script holds the address of the heap from that heap leak. As I mentioned, this binary just leaks the heap for us, which is a bit of a gimme, but heap exploitation can lead to leaking of heap and libc addresses. So we can use heap for the address of the heap. The elf object represents the binary. Elf.sim allows us to access symbols from the binary, which, as I mentioned, is non-pick, so we know where they are at all times. So elf.sim.target, that target data is matched to the target symbol in this binary. Lastly, we have a malloc helper function that I've written that just wraps that malloc option in the binary. So for example, calling that malloc helper function is the equivalent of hitting 1 to request malloc. Then the first argument is its size, hex 18 or 24 bytes in this case. Second argument is the data you want to send, so this sends 24 capital A's. There's also a delta function that we'll deal with shortly. So go ahead, delete all of that stuff. That's why we made a copy. And we're going to start by emulating what I just did in GDB. So we use a malloc wrapper function to request, I'm going to go for a minimum size chunk. You guys can make the chunk whatever size you want. Just bear in mind that you're going to have to write that amount of data to overflow it. And then I'm just going to write 24 bytes of garbage. That's going to fill up the user data of that chunk. Anything we write over and beyond this is going to be part of the overflow, and it's going to overwrite that top chunk size field. So because we can't concatenate strings and integers, we're going to use the p64 function, short for pack64. It's a PwnTools function that is essentially a wraparound struct.pack. And that means we can just send like a 64-bit integer, and we don't have to do \x a bunch of times, and we also don't need to care about endianness, because it's going to deal with it for us. So we might as well set the top chunk size field to the largest possible chunk size, or the largest possible valid chunk size. So that would be 0x with 15 Fs, and then a 1 on the end. Don't forget to close the brackets after that as well. So once you've copied that down, go ahead and run this script on the command line. It's executable. You don't need to write Python and then the script name. You can just do / name of this script. If you're using Vim, you can do bang /% to run the script as well. And what PwnTools will do is start the binary, and then it will send it the data that we've requested it to. So it's going to make a request for a minimum size chunk, and then it's going to send that data. And then it will return control to us via an interactive shell. So I'm going to go ahead and run mine now. And it's going to decide it's going to check for newer versions of PwnTools, which is just fantastic. So that's going to waste a moment of our time, despite having run this several times up until now and not had this come up. Oh my word, are you going to do this every single time? Bear with me. Never too late to fix things on the fly. Alright, if it does that again, I'm just going to have to fix that real quick. So I've got an interactive shell, and we can see that our script has requested that chunk on our behalf. Happy days.
Sorry, I missed how you sort of started. So I've created the file, and then you said that's already executable. So I should just be able to run exploit.py, yeah?
Yes, that's correct. Yeah, so I'm running mine from inside Vim. If you are using Vim, like I say, you can use the bang /% command. Yeah, so just at the bottom of the screen there, if you hit, you can hit return instead of colon in this version as well. And that'll just run whatever script you're using. Like I said, they're executable. So, all right, seems to be playing the game now. So that's pretty useless though, because we can't introspect memory. So if you go back to your editor.
Sorry, one question. I get a IO interactive.
Well, when running this.
No, that's all right. That's all right.
Yeah, you might have a missing bracket or something.
Yeah.
Awesome. So this time, run the script again on the command line with the GDB option. So / name your script space GDB all uppercase. This time, PwnTools is going to run that binary, attach GDB to it, and then drop us into an interactive shell. So we can Alt-Tab, or if you're on a MacBook, Option-Tab between the binary and interact with that and GDB. We can use Control-C to break in GDB, and then we can use the viz command to introspect our process's memory. Heap memory, I should say. And we can see that it's done exactly as we expect. It's written 24 capital X's into that chunk's user data, and then it's followed that up by writing a very large integer over the top chunk size field. So now we can move on to phase 2. Incidentally, you might notice that these heap addresses here aren't what we were seeing earlier on, and that's because we attached via GDB. So this is now subject to ASLR. If you guys want to keep those friendly addresses, You can run the script with the no ASLR options as well, which make debugging a whole lot easier, especially if you're using hard-coded addresses. So if you run your script with the GDB and no ASLR options, if I break GDB with Control-C and then viz, we can see that we get those sort of friendly hex 405000 addresses. So the next stage is making that large request. Now that we've tampered that top chunk size field, Malloc thinks that the top chunk is huge and it wraps around the VA space. So now we want to make a large request that spans the gap between the heap and our target data, stopping just shy. We're going to use that delta helper function to do this. Delta takes two arguments, the start and end addresses that you want to wrap around. And all it does is calculate that wraparound, that so-called wraparound distance between those two addresses. So we want to request a chunk using Malloc, and we want the size to be delta, and then we want the delta between the heap and because that's the heap start address, we actually want the delta between the top chunk and our target. So the heap plus hex 20, because we requested a 20 size chunk. If you guys requested a larger chunk, you'll have to change that value to the appropriate size, so 3040, etc. So the address of the top chunk, and then we want the delta between that and our target, which, as I mentioned before, elf.sim.target, which is the elf object, symbols, the target symbol. And we want to stop just shy of that, so we're going to add a minus hex 20 on top of that as well. And we're going to send an empty string as the data using this call to our malloc helper function as well. So I'll give you a moment to copy that down. Once you've got that copied, go ahead and run your script with the GDB and, if you want, the no ASLR options as well. Everybody happy with that? All right, so we can Alt-Tab or Control-Tab back to the Option-Tab back to the binary and see, hit Enter a bunch of times. It's still running, hasn't crashed, and PwnTools has requested two chunks for us. We can Alt-Tab back to GDB, hit Control-C. Don't use the viz command now, Pwnbag will have a right meltdown. Instead, we're going to use DQ for dump quads, target minus 16. So dump quad words at the target symbol, that's the target in our binary, minus 16, so we're just going to introspect the memory just prior to that as well. A DQ target minus 16. And here we can see our target data at address hex 404010, those hex 58 bytes representing those capital X's. And there's a suspicious value in the quad word just before it here, that 1011. So we can use Pwnbag's top chunk command to figure out where Malloc thinks the top chunk currently resides. This pink address hex 404000, which is right here, making this value here the top chunk size field. So hopefully the next request that we make is going to get broken off that top chunk, and its first quad word of user data will overlap our target data. And we can just do this manually. If you hit C for continue, Alt-Tab back to the binary, hit 1 to make a request. I'm going to make a minimum size request, and then I can just write some data over the target. Hopefully, when I request the target, instead of printing those capital X's, prints whatever data I sent. And don't forget to close your debugging session. We can just add another line to our script to consolidate that. So one more request to Malloc for a minimum size chunk, and then whatever we write into the data of that chunk is going to end up overwriting our target data. So I'm just going to go for Malloc 24 minimum size chunk and then the string much win. We can run the script this time without the GDB and no ASLR options, so under production conditions to see if it works. And then I can pick option 2 to print the target, and indeed, the target's been overwritten. So that's how you can leverage the House of Force technique.
Could you just bring up the script again?
I can indeed. That's how we can leverage the House of Force for an arbitrary write. So in summary, this binary had a small heap overflow that allowed us to tamper with that top chunk size field. We set it to a large value, tricking Malloc into thinking that that top chunk spanned a lot of the rest of the VA space. And then we made a large request that spanned the gap between the top chunk's current location and our target data. In this case, our target data was a lower address than the heap, but that didn't matter because we were able to wrap around the VA space. And then lastly, we made a smaller request that overlapped our target data, at which point we were able to overwrite it. So some of this stuff might be dependent on what kind of primitive you can get out of the binary. So you may not be able to write to these smaller chunks, but you can potentially read from them. So reading or writing to sensitive data or just corrupting it. If you're attempting to tamper data on the heap, you don't necessarily need that heap leak because, of course, as we've seen, the heap is deterministic, so the distance between the top chunk and data on the heap will be relative. So you can wrap around back onto the heap itself without having to leak the address of the heap. Because, as I said, it's a relative distance that you're wrapping around. So it depends what you're using it for, basically. Now, because these workshops got changed around today, we haven't got time to drop a shell on this binary, sadly. But if for whatever reason you couldn't get that one working, there is a file called .pwnTools solution target in this folder. All that does is exactly what we just did, and it's got a bunch of comments on it as well, if you guys want to review this kind of stuff later. There is also a .pwnTools solution shell script. Now, sadly, we don't get to cover this right now, but this will show you how to drop a shell with this technique, changing an arbitrary write into dropping a shell via system bin share. So you guys can check that out later if you fancy. All right, let's move on to our second technique, the fast bin dupe or duplication. We'll start with some more Malloc internals. Now, one of the things that Malloc does very efficiently is recycle unused heap memory. And this is achieved via the second of Malloc's functions we're going to look at right now, free. Free is another dead simple function. You pass it a pointer to a chunk that you no longer need, and then you can forget about it, safe in the knowledge that that chunk will be recycled if and when is necessary. But from Malloc's perspective, that chunk will be linked into one of several free lists, which are, as they sound, lists of free chunks. Of particular interest to us right now are a collection of these free lists known as the fast bins. Fast because the free chunks in these lists are recycled fast, and bins because that's what the Malloc maintainers like to call lists when they feel like it. And the fast bins are just a small collection of singly linked, non-circular lists that each hold free chunks of a specific size. And to help us visualize how the fast bins operate, we're going to debug another small demo binary. So once again, switch fire to your VMs, navigate to the fastbin dupe directory, and we're going to debug the demo binary again under GDB with the command gdb demo. Once again, issue the start command to kick things off once GDB is launched. And we can see from the source panel that the first thing this binary does is request 3 minimum size chunks. We can pass the number of lines that we want to execute as an argument to next, so next 3 will execute those 3 lines, issuing those 3 requests. We can follow that up with the viz command to introspect the heap, and it looks exactly like we'd expect it to, with 3 minimum size chunks, these 2 1 size fields here. Chunks A, B, and C as labeled by the program respectively. We can use the context code command to check out that source panel again, and we can see that the next thing this binary does is free those chunks in order A, B, and C. So before we let it do that, we're going to introspect the fast bins using pwnbag's fastbins command. And we can see from the output that, under default conditions at least, each heap has 7 fast bins associated with it. The 2.0 fast bin, for example, exclusively holds free chunks of size hex 2.0. 3.0 fast bin holds 3.0 size chunks, etc., up until hex 8.0. So let's go ahead and use the next command to free that first chunk, that yellow chunk, chunk A. Now we're going to issue the fastbins and viz commands back to back so we can see what's changed. First thing we notice is that chunk A has been linked into the 2.0 fastbin. Chunk A was a hex 2.0 size chunk. Its address is hex 405000. Recall that even though chunk A's user data starts here at this quad word, Malloc considers it to start here. So the address hex 405000 has been linked into the 2.0 fastbin. That's also annotated here in the output of the viz command. But there's no other visible changes on the heap. And that's because not all of Malloc's metadata is stored in line. The head of each of these fastbins resides elsewhere in memory in a structure known as an arena. And arenas are large structures that primarily consist of the heads of each of Malloc's many free lists. So when we freed chunk A, its address was written to the 20 fast bin slot in this heap's arena, which, as I mentioned, is elsewhere in memory. In libc's data section, in this case, because this is the default heap, and it uses a special arena called the main arena. So let's go ahead and see what happens when we free chunk B, the turquoise one. And then we'll follow that up with the fastbins and viz commands. Now we can see that chunk B, which Malloc considers to start here, has been linked into the head of the 20 fastbin. So chunk B's address has been written into the 20 fastbin slot in this heap's arena. But there's only one slot for each fastbin per arena. The rest of that 20 fastbin's metadata is held on the heap. And we can see that the first quad word of chunk B's user data has been repurposed, since this is now a free chunk, it doesn't need to use its user data anymore, as a forward pointer, or FD. And that points to chunk A. Chunk A's FD is null, indicating the tail of the list. We can see that annotated to the right of the output of the viz command here, so 20 fastbin 0, as in the head of the fastbin, and then chunk A is now the second chunk in the 20 fastbin. Annotated up here, chunk B, chunk A, with a null terminator. So just to consolidate, we'll free chunk C, issue the fastbins and viz commands, and we can see that, as expected, chunk C at address hex 405040 here, this purple chunk, that Malloc considers to start here, is now the head of the 20 fastbin, so its address has been written into the 20 fastbin slot of this heap's arena, elsewhere in memory. Its the first quad word of its user data has been repurposed as a forward pointer. That points to chunk B here. Chunk B's forward pointer points to chunk A. Chunk A's FD is null. So now, using the context code command, we can see that the last thing this binary does is request 3 more minimum sized chunks, labeling them D, E, and F. So we're going to use next 3 to execute those 3 requests. And then lastly, we're going to do fastbins and viz to see what's gone on. First thing you'll notice is that we've still only got 3 chunks on the heap, despite having requested 6. And that's because allocations from the fastbins take precedence over allocations from the top chunk. And the 20 fastbin is empty. So those 3 chunks got allocated, and we can use print D, print E, and print F, which shows us that we got, this time, the user data addresses, because these are return values for our program, of chunk C, purple chunk B, and then chunk A at hex 405010 here. So we've got those chunks back in reverse order that we freed them, and that's because fastbins are last in, first out, or LIFO structures. So very simply, they can be thought of as stacks of free chunks of the same size. So every time you free a 20 size chunk, that'll get added to the top of that 20 fastbin stack, as it were. And then any chunk you add on top of that will get added to the top of it. And then when you allocate chunks of 20, or when you request 20 size chunks, if that fastbin has any chunks in it, then those chunks will get popped off the top of it, and Malloc will give you those back rather than requesting more memory from the top chunk. And that's how Malloc recycles its memory, at least with chunks of size 20 through 80, so-called fast chunks. So with how the fastbins work in mind, we're going to close GLIBC with Control D, or quit. And once again, we're going to run our vulnerable binary fastbin dupe. Give you guys a moment to have a play with that. Similar sketch as before, small CTF-style binary written in C. It's got a different type of heap bug this time. And once more, we're going to leverage that to learn and then perform the fastbin dupe technique to make an arbitrary write. And while you're doing that, I'll explain what's going on. Once again, I'm going to run my binary under GDB with GDB fastbin dupe. And I'm just going to run with the run commands. This time we get a libc leak, which will only be used if you're dropping shells. We didn't use that last time because we don't have time to drop shells, sadly. Then it's going to ask us for a username. I'm just going to put any old garbage in there for now. And then this time from our numbered menu, we can see that we can request up to 7 chunks via the malloc function, option 1. So I'm going to request a chunk. But this time we're limited to fast chunks only. So 120 bytes maximum, that'll give us an 80 size chunk. So any request size between 0 and 120. So we can only request those fast chunks that will be linked into the fast bins when we free them. So I'm going to request another minimum size chunk, send some data to it. This time option 2 allows us to free these chunks by index starting at 0. We can't free out of bounds indices, but I can free the first chunk that I requested at index 0. If I hit Control C in GDB, the fast bins and viz commands show us that, as expected, I got that 2.0 size chunk requested for me. This was my capital Y's, that data I sent, with this new line here. But because we freed it, that first called word user data has been repurposed as a forward pointer and been nulled out. And we can see that that chunk that I requested has now been added to the fast bins. So we can free these chunks, add them to fast bins. Lastly, option 3 prints that target, once again, short string of capital X's in the data section of this binary. There is a slight wrinkle here. If I Control C, I'm going to DQ for dump quad, ampersand user. That's going to print the user struct. This time our target here, these capital X's represented by the hex 58 bytes, is part of a larger struct called, that it's just arbitrarily named user struct. That holds our username that we inputted earlier, followed by our target data that we want to overwrite. So there's just a slight change this time. So has anybody found the bug? Well, I'll tell you that this time we have a double free bug. Double frees are scenarios whereby you can coerce a program into freeing the same chunk twice or more without allocating it in between. And this is a common bug. There are some weird ways it can manifest, like using realloc. You don't even have to explicitly be calling free. And they sound benign to begin with. Freeing the same chunk twice without allocating it, so what? But if you free that same chunk twice without allocating it, it's going to get linked into the same fast bin twice. Meaning that later, potentially, it will be allocated for 2 different purposes simultaneously. So, for example, if I freed that 2.0 chunk that I requested a second time, so that it was in the 2.0 fast bin twice, it might get allocated once to hold some benign user data, for example, that I as an attacker had control over. And it might also be allocated later after that to hold something sensitive like an admin password hash, at which point I could read from or write to that sensitive data because I had an overlapping chunk. So let's try that with this binary. I'm going to try and free that chunk 0 a second time. And we got a SIG abort. Now, processes don't normally issue abort signals. If you get an abort, it's because GLIBC has caught you out doing something that you shouldn't. And indeed, if we scroll up, we can see this error message here, double free or corruption brackets fast top. So it's detected this double free scenario. The fast top's a little more cryptic. How this double free mitigation works is every time you free a chunk into a fast bin, Malloc will check to see whether that chunk is already at the top of that fast bin stack, at the head of that fast bin. If it is, clearly that's a double free scenario, and GLIBC will abort because, as I mentioned, it's potentially a dangerous situation having a double free. But this is the only bug we have to work with here, so we're going to have to get around this mitigation somehow. Any ideas? Well, I'm going to run the binary again, spam any old data into username. I'm going to request 2 chunks this time of the same size. I'm going to go for minimum size chunks. Then I'm going to free chunk 0 into that 2.0 fast bin. So fast bins and viz command show us that I've got 2 chunks. That first one has been freed into the 2.0 fast bin. If I free that chunk again using our double free bug, we'll get checked with an abort. But it's only checking to see if that chunk is the head of that 2.0 fast bin. So what if we just free a different chunk at index 1 into that 2.0 fast bin? So now, chunk B, or chunk at index 1, is now the head of the 2.0 fast bin. So technically, if we free the chunk at index 0, we don't get checked. And that's still the case. If I Control C and VM map, you can see that the version of GLIBC we're using is it's a no Tcache version, which is something that's covered on a different course. But this is GLIBC version 2.30. This is the very latest version of GLIBC. We're not using like an old, like 2.19 or anything. This is compiled the very latest version of GLIBC. which I think most distros, unless they're rolling distros like Arch, won't be using right now. Like 2.27 is in the latest version of Ubuntu long-term support, so 18.04. So this is still something that you can do under modern versions of GLIBC. The last one we were using was, I believe, 2.28 as well, which again is more modern than the latest Ubuntu long-term support. So these aren't just old useless versions of GLIBC we're using. This is the very latest stuff. Anyway, so we can still double free despite that mitigation. And that's what we're going to do. That is a fast bin dupe. Technically, that's it for the technique. You're just duplicating a fast bin. But we're going to leverage that for an arbitrary write. And once again, to do that, we're going to use the Pwn Tools library so that we can do things like send on printing bytes and make this repeatable. So close GDB with Control-D or quit. And once again, make a copy of that Pwn Tools template script without calling it pwn.py. Open your copy in your editor of choice. And again, scroll down to the bottom where we have some example stuff. Leave the example stuff there this time because we're going to make use of it. First thing this script does is deal with the username. We'll set it to George. Why not? Then it's going to request two 3.0 size chunks. That's an error. And it's going to label them chunk A and chunk B. The malloc helper function in this script returns the index of the chunks that it's allocating, just using a small counter in the script itself. So that instead of remembering which indices we're trying to free later on, we can just label them with Python variables. So we can then free chunk A here, for example, rather than saying free 0. So chunk A and B are two 3.0 size chunks, and it's going to spam a bunch of data into each of those size fields. And this is more or less those data sections, sorry. So this is more or less what we just did. All we need to do is add another free to free chunk A. So go ahead and do that. And that is the equivalent of double freeing that chunk whilst bypassing the mitigation. And indeed, if we run this script with the GDB and no ASLR options, we can Control C in GDB. And now the fastbins and viz output shows us that we have confused things. I mean, technically, we've turned a singly linked non-circular list into a circular list. So chunk A, that yellow chunk, is linked into the head of the 2.0 fastbin. Its forward pointer, that first quad word of user data, has been repurposed for it. That points to chunk B, hex 405030 here, which is what malloc considers chunk B. But chunk B's forward pointer points back to chunk A. And we can see that Pwnbag sort of tried to annotate it here and here slightly confusingly. But if we were just to keep requesting these chunks back and forth, we'd just keep getting chunk A and B because malloc doesn't explicitly clobber that data when you request stuff. So we just keep getting chunk A and B back. So we've created a fastbin dupe, a double free scenario here. But the example I gave before is useless, right? There's no admin password hashes here. All of the data on the heap that we control is our own. Plus, we want to turn this into an arbitrary write. So instead, what we could do is request chunk A, that yellow chunk, back from the 3.0 fastbin in this case, keeping a copy of it, as it were, even though there's only one chunk A, keeping it linked into that 3.0 fastbin. And then, because we've allocated it back to ourselves, we're now able to write to its user data again. Can't write to free chunks unless that's a different bug. But because we've allocated it, we can start writing to its user data again. But that first quad word of its user data is still being used as a forward pointer in the 3.0 fastbin. Because chunk B will then be the head of the 3.0 fastbin, its forward pointer will point to chunk A, and then chunk A's forward pointer will point, potentially, wherever we want to point it. And we can point chunk A's forward pointer to a fake chunk overlapping data that we want to overwrite. So let's go ahead and do that now. We can Control-D to quit from GDB. And then we want to make a request for a 3.0 size chunk. I find the best way to request chunks of size that you want is to get the chunk size, so hex 3.0 in this case, and just take 8. Because that will be the maximum amount of user data that you can hold in a chunk. So if I want a 3.0 chunk, I get 3.0, take 8, hex 2.8. It's the easiest way to remember how to allocate chunks of a specific size. So we want to grab chunk A, and then we want to use pack64 because we're writing addresses, and we want to account for endianness. And we want elf.sim.user in this case. Remember that the target is part of that user struct. Fortunately, the user struct starts 16 bytes prior to the target, so we don't need to go target minus 16 like we did to account for the fact that Malloc considers its chunks to start 16 bytes prior to its user data. And then close those brackets. And then, once again, you can run the script with the GLIBC and no ASLR options. Break with Control-C, and then fastbins and viz show us that chunk B is now the head of the 30 fastbin, followed by chunk A, and then our fake chunk, a hex 404010, overlapping our target data. So we can just dump quad that address, and we can see that that is the user struct with our target data. So now what we need to do is request chunk B and chunk A, and then the next chunk to come out of the 30 fastbin will be our fake chunk overlapping the user data, overlapping our target data. So let's close GDB with Control-D, head back to our editor, and make 2 more requests for a 30 size chunk. I'm just going to stick any old data in there. And then once you've added those 2 lines, run your script again with the GDB and no ASLR options. So you're just requesting 2 30 size chunks. All these chunks got to be the same size to get rid of those chunks A and B, and so to ensure that the next chunk that gets allocated is our fake chunk. I'm going to do that now. I'm going to hit Control-C to break, and then fastbins and viz show us that now the next chunk to be allocated from 30 fastbin is going to be the chunk that overlaps our target data. Awesome. So we can do that manually. C for continue, Alt-Tab. I'm going to request a 30 size chunk. However, we get an abort again. We've tripped over the second of Malloc's exploit mitigations that we're going to have to deal with today. This one's a little more cryptic. The error message for it is just memory corruption brackets fast. This one is checking the size field of the chunks it allocates. Because if you're allocating a chunk from a fastbin, those fastbins will only ever be holding chunks of a specific size. So if you end up allocating a 50 chunk from a 30 fastbin, something has gone very, very wrong. And that's what Malloc does. Before it allocates us that chunk, it's going to check the size field to make sure it matches so that it's a 3-1. And then if it doesn't, we get an abort. Fortunately, in our case, if I run that again, you guys don't have to do this. If I dump quant ampersand user, I haven't given it time to do that. This, if you'll recall, is our username field. So we control this data here, and we can potentially set up a fake size field prior to our target. And that's exactly what we're going to do. Now, in this case, we're very fortunate. We can control this data with good accuracy just prior to our target. But we can do chunks up to hex 80, for example. So it doesn't have to be right up against it like this. It can be 120 bytes, give or take, just prior. You can also coerce existing data into fake size fields as well. So, if you head back to your editor, and this time set the username to, I'm going to go for pack640, which is just to fill in that first useless quad word with a null, followed by pack64 and then our size field, so hex 31. And then once you've done that, run the script again with GDB and no ASLR options. Oh, sorry, the change was this line here. And I changed the username from George in quotes. I deleted all of that and I added 8 bytes of garbage, which an easy way to do that is just pack640. So that's a null because we can write nulls in this case. And then pack64 hex 31, which is our size field. And then go ahead and run that with the GDB and no ASLR options when you're ready. Now, if I dump quad user, you can see that we've set up that fake size field. And if I manually Alt-Tab back to the binary and try and request a hex 28 chunk, it goes through. And I can write some arbitrary data, which, when we check the target, has overwritten our target data. And just for the sake of completion, let's add that to our script. So we can request a a hex 30 size chunk out of that 30 fast bin. That overlaps our target data, and then anything we type there is going to end up overlapping our target. And then when you run it, you can get rid of the GDB and no ASLR options to run it under production conditions. And then when I print the target, we've overwritten that data. So, in summary, this binary had a double free bug. We were able to leverage that double free by bypassing a fastbin's double free mitigation. So instead of just double free in the same chunk, which incidentally you can do in a lot of other like memory allocator implementations. So for example, Android, I think since, I'm going to go for version 7, I think uses gmalloc or gemalloc. That has no double free protections or anything like this. GLIBC, the reason I teach the GLIBC stuff is because all of the mitigations are in GLIBC. Because it's been around for the last 30 years. It's, if not one of, it's the most heavily protected memory allocator. But as we've seen, even in the most recent version, you can still kind of dodge this stuff. It depends on what kind of control you have, basically. We're lucky in this case. We've got these little CTF style binaries. We can allocate and free as and when we fancy, but it's not always that simple. All right. I think we've got time to drop a shell on this binary. I'm just going to go for it. It might be a bit of a rush, but yeah, screw it. Is everybody happy with that? Okay, because there's a nice little trick you can do here. Okay. Make a copy of that script. Again, if you can get it working, there is a .pwnTools solution target script. What we're going to do is make a copy of that, as I say, or I'm just going to edit this one, delete that last line. And what we're going to do is I'm going to quickly introduce the Malloc hooks. Now, we have an arbitrary write here, and we want to turn an arbitrary write into arbitrary code execution, right? So what could we overwrite? Return addresses on the stack, potentially, but we can't leak the stack in this scenario. I'll leave that there for now. The binary has got PLT entries and Finney array, but if you checksec this binary, you can see that it's compiled with full rel-row, which means those sections are going to be mapped read-only after initialization. We could hit libc. That's got PLT of its own. It's got exit funcs. It's got TLS detours, but they're both protected by exit funcs and TLS detours are protected by pointer mangle nowadays, and it's difficult to reliably trigger the stuff that's in libc's got PLT. But what we can do is leverage heap-specific functionality to get arbitrary code execution. I'm talking about Malloc's hooks. Every core function in Malloc has an associated hook. So there is a Malloc hook, and there is a free hook, and some others. And the idea of those is that Malloc uses them for initialization, and programmers can use them to implement their own memory allocators or collect Malloc statistics. They are a writable quad word that essentially serves as a function pointer in libc's data section. And they remain writable for the entire duration of the program, regardless of whether there's full rel-row implemented on the binary or not. And the idea is that every time you call one of the core functions, so you call free or malloc, every time, say, you call malloc, the malloc function will check that malloc hook to see if it's null. If it's null, the call goes through to malloc normally. If it's not, that value is treated as an address, and execution is redirected to that address. And we're going to leverage that to get arbitrary code execution. So, let's do this in 13 minutes. All right. So this line here, where we redirect where we overwrite that 30 fastbin forward pointer, we're going to change that to libc.sim. And then the symbol name for the Malloc hook that we're going to use is __malloc _hook. And the idea is, what we want to do is do the same trick that we just pulled to overwrite this target data on the Malloc hook. We could choose the free hook as well. We're not gonna, because we'll see why shortly. Free hook is often a better choice if you can hit it, but I'll have to explain that later. So we can make an arbitrary write over this Malloc hook, then we can point that to, say, like libc's system function or something like that, and then every time we call malloc, instead of malloc getting called, system, for example, will be called. So let's run this with the GDB and no SLR options, and then we are going to Control-C and then fastbins. We can see that now, instead of that fake chunk over our target data, we have a fake chunk overlapping the Malloc hook, just like before. However, if I dump quad ampersand underscore underscore Malloc underscore hook, the Malloc hook is this value here, that B50 value. I'm going to do minus 2. Again, I am rushing this a little bit, but it's worth it. So that 7B50 value is the Malloc hook. So currently it's null. If you manage to catch it before initialization, Malloc will have that pointed to some initialization functions, but that will null it. And then for the rest of the program's duration, under normal conditions, that will just be null. So every call to Malloc just goes through to Malloc as expected. And this is where that size field would normally sit, right? Remember, the only way we were able to allocate that fake chunk is because we were able to coerce a size field. But that's a libc address. We're never going to be able to request a chunk of that size, especially in this case when we can only request fast chunks. It wouldn't qualify for the fast bins anyway, and we can't mess with this data because it resides in libc's data section. And we're doing this for an arbitrary right. We don't have that arbitrary right already. However, there is reliable data here. You'll notice that when we VM map, all the libraries are loaded at 7F addresses. An ASLR on a 64-bit system isn't as robust as it seems. The least significant 12 bits will always be static under 64-bit ASLR because it only has page level granularity. So everything from here onwards. And the first 3 bytes of a library will always be 00007F. So it only really affects these bytes in between. So even under ASLR, we do have some realistic bytes. And for the sake of time, what I'm going to do is dump quads, and I'm just going to cast the address of the Malloc hook as a car star, and then I'm going to do minus hex 23. So interestingly enough, Malloc isn't quite as robust again as it seems. It doesn't necessarily check, even though the free function will, Malloc won't check if your chunk is aligned. So we can create misaligned fake chunks anywhere in memory that we like. So for example, if we were to create one at the Malloc hook minus hex 23, there are 2 values that I just showed you. In fact, we need to go slightly further back. So there are 2 values here that will always have reasonably reliable values. So for example, this value here is actually the vtable pointer for, I believe, the standard in IO wide. That's standard in's IO wide vtable pointer. And standard in is part of the standard IO, standard in, standard out, standard error. They are impossible to get rid of. Firefox has those things, and you're not interacting with that over the command line. So this value will always have a libc address. And even though it will be subject to ASLR, these bytes here will always be 00007F. So we can misalign a chunk to catch a bunch of nulls and then follow that up, well, a bunch of nulls, I think it's from the previous quad word that we need. This quad word here will also always be null because that's a padding value. There will never be anything here. So what we can do is we can misalign these values, and we can catch 5 of the least significant bytes out of here, or 5 of the most significant bytes out of here, 3, and then we can wipe out 5 of the least significant bytes of this value here, and I know I'm going fast, and then we end up with that effect of creating a 7F value here. And we can do this every single time, regardless of where these libraries are loaded in ASLR, because those values will always be present, and they will always be a 7F address, and they will always be a null. And again, 7F isn't a valid size field. Remember that those low-order nibbles are used for various flags. But it turns out 7F can still be used, because Malloc won't check that 4th least significant bit that isn't even a flag. And it just so happens that this combination of flags will still work. So we can create a 7-0 size chunk that overlaps the Malloc hook, even though we can't edit the data there. So if we head back here, we can do minus hex 23. And then what I'm just going to do is change all of those hex 28 size fields to hex 68 so that we get 7-0 size chunks instead. And now, when I run this with GDB and no ASLR, our 7.0 fast bin contains this value. And if I dump quad there, we can see that now this chunk has a valid 7.0 size field, even though we weren't able to tamper that data, and it overlaps the Malloc hook. So all we need to do now is request a 7.0 size chunk. We need to spam this much garbage, and then whatever follows that is going to end up with, it's going to end up overwriting the Malloc hook. Now, in some situations, you might be able to overwrite it with like a pointer to system or something. libc's system function, you pass it a pointer to a string, and that string is interpreted as a shell command. In this case, we can't do that. Sometimes if you can allocate arbitrarily large chunks, you can trick Malloc into passing the size field, which is masquerading as an address, an address masquerading as the size field, to system. So any arguments that we pass to Malloc will be passed through to system in that case. But because we can't request arbitrarily large chunks here, we're going to have to figure out a different way. And we're going to use a one gadget. So one gadgets are pieces of code in libc that execute a shell. So for example, libc's system function does the equivalent of execve bin sh with the -c option and then your string. So there are pieces of code in libc that just do the equivalent of execve bin sh. And a chap called David942j has written an awesome one gadget finder that uses symbolic execution to find these things in versions of libc. So what we can do is point it at our filespin dupe binary, and you guys don't have to copy this. And we can run the one gadget finder against that version of libc. And it will tell us the offsets from the start of libc of each of these equivalent execv bin sh pieces of code and their constraints. We're going to skip ahead, and I'm going to tell you that this constraint here with stack pointer plus hex 50 being null is the one that's going to work for us. So hex E645B, and we're going to do libc.address plus that value, and then that'll overwrite the Malloc hook with the address of a one gadget, and you can see that call to execv there. So hopefully next time we call the Malloc function with any old size, as long as it actually gets called, we'll see it detaching from processes, etc. We get a shell. So what we did there was create a fake chunk overlapping the Malloc hook, because that fake 7f size field will essentially always be present if we create that sort of sliding window effect, basically. And again, we can run this without the GDB and no ASLR options to ensure that it works under default conditions. I'll tell you what, let's add that last line to Malloc, and then any old size with an empty string. And then we get a shell out of it straight away. That'll work every time. Doesn't matter what things get loaded where, etc., etc. This is all running under ASLR. So there you go. Apologise for that being fast. I didn't think I'll be able to squeeze that bit in, but we've just sort of made it. Again, there is a .pointtool solution shell script in this in this directory. That's got a bunch of comments that actually gives you a bit more detail on what I was rambling on about there real quick. But I thought you guys might appreciate that. That brings us to the end of the workshop, guys. If you've got any questions, there'll be another workshop in here in a minute, so I'll have to shoot, but I'll be hanging around for the rest of the day. If you fancy learning more GLIBC heap exploitation stuff, I teach a 2-day training course on this stuff. It's called HeapLab. Covers a bunch more techniques from like the old school unsafe unlink to the very cutting edge, very latest versions of GLIBC. That's running at 44 Cons training in March and in Ring Zero in Vegas in August as well. Thanks for coming, guys. Hope you enjoyed it. Cheers.